We begin this transmission module by looking at the clutch system used with the manual ZFS-636 gearbox. The drive input from the engine to the ZF manual gearbox is via a single-plate diaphragm spring clutch designated KB114B, which stands for K clutch, B Borg Beck, 1 single plate, 14 14-inch disc diameter, and B the development code. Clutch control is by a conventional hydraulic master and slave cylinder system. In order to reduce clutch pedal load during disengagement, the clutch pedal has an over-center pivot action. When the clutch pedal is in the off position, this spring is acting directly through the pedal pivot point. However, when the clutch pedal is in the release position, the spring is assisting the pedal with disengagement because the spring forces are now acting with the pedal. The remainder of the clutch hydraulic system is the clutch slave cylinder. From a maintenance point, the clutch pedal should have a clearance of 4 to 5 millimeters when in the off position. Clutch control. The clutch slave cylinder is of the clearance-free type. With the clearance-free system, the operating piston in the slave cylinder is spring-loaded outwards. When the linkage is preset, the front of the piston takes up a position some 15 millimeters from the outer face of the cylinder. This positioning allows the right amount of lever movement for full clutch disengagement. With the clutch cylinder preset in this way, a wear clearance of 20 millimeters is created between the rear face of the operating piston and the back of the slave cylinder. As the clutch wears out, the outward pivoting action of the diaphragm on the cover assembly pushes the release bearing, fork and operating lever backwards. With this rearward movement also acting on the operating piston, the 20 millimeters wear clearance to the back of the cylinder progressively reduces down to 0, at which point, if left unchecked, clutch slip would develop, resulting in premature failure. Monitoring the wear clearance is therefore of the utmost importance from a preventive maintenance point of view and should be checked a minimum of every 3 months. To establish the wear clearance within the cylinder, first of all, measure and note the distance between the front of the cylinder and the center of the clevis pin. With a suitable lever or wrench, press in the push rod until the piston bottoms on the back of the cylinder. Then measure and note this new distance. The difference between the two is the amount of wear clearance which is left. When the wear clearance approaches 5 millimeters, it's time to reset the piston position within the cylinder. Clutch cylinder resetting. To reset the clutch cylinder where the piston wear clearance has reduced to between 5 millimeters and 0, first of all, slacken the lock nut on the push rod yoke. Unclip and remove the clevis pin, then move the yoke clear of the lever. Due to the internal spring action, the yoke and push rod will be moved outwards until the operating piston comes into contact with the retaining clip at the front of the cylinder. Wind the nut back approximately 10 millimeters where possible, then screw the yoke in until it meets the nut. Realign the yoke on the lever. Refit and reclip the clevis pin. Then finally, retighten the lock nut. With this resetting, the wear clearance would now be reinstated. Be aware that with periodic resetting, the lock nut will eventually run out of adjustment on the push rod. In this condition, when the operating piston wear clearance reduces to 0, the clutch center plate must be replaced. Another important basic setting is the clutch operating lever, which should be positioned approximately 65 millimeters from the center of the clevis pin on the push rod and the bell housing to gearbox casing face. In this position, the lever will be pointing approximately 5 degrees rearward from vertical. This positioning is important from the point of view of base setting the clutch lever following clutch replacement. Having set the clutch lever, it will be necessary to adjust the basic setting on the slave cylinder. This is done as follows. Before connecting the push rod to the release lever, move the yoke clear of the lever allowing the operating piston to be pushed to the front of the slave cylinder. Adjust the yoke until its clevis pin center is in a position 15 millimeters ahead of the lever clevis pin center. At this point, the yoke can be realigned with the lever and the clevis pin refitted and the lock nut tightened. As stated earlier, this 15 millimeter setting at the operating piston is to allow full clutch disengagement to take place. To assist in this resetting, this special tool is available from Volvo. These pins are 15 millimeters between centers, so base setting is made even more simple. Bleeding the clutch. Due to the design of the master cylinder, the clutch hydraulics must be power bled. This is done using the reverse bleed method, which pumps the clutch fluid through the bleed nipple on the slave cylinder, along the fluid line and into the reservoir via the link channel in the master cylinder. The prescribed method utilizes a windscreen washer pump piped to draw fluid from a container, then pump it into the slave cylinder. The motor is connected to a voltage supply from the battery and controlled by a switch. To ensure the pipe does not blow off during bleeding, this simple adapter is used to clip the hose onto the slave cylinder bleed nipple. An assistant should be used to monitor the level in the reservoir to ensure it does not overflow, remembering that clutch fluid is a solvent and can seriously damage paintwork. It should be noted that only clutch fluid with the specification of .4 may be used when replacing or topping up. Module 4, Transmission Systems. Section B, ZF S6-36 Manual Gearbox. Let's now move on to the first of the three gearbox options offered to the B6. The ZF S6-36 is a 6-speed synchromesh gearbox which has a forward gear ratio spread ranging from 7.4 to 1 for first gear through to 1 to 1 in sixth. The gearbox is conventional in layout with an input shaft, counter shaft and main shaft. The input and main shafts are supported on roller bearings, whilst the counter shaft is on taper roller bearings. The idler gears on the main shaft are supported on needle roller bearings. Gear selection is by synchronized sliding coupling sleeves. Control from the gear lever is via two cables. One cable creates lateral movement across the selector gate, while the other is for gear engagement. Manual gearbox maintenance. Generally speaking, the gearbox oil should be changed every 12 months. Refer to the lubrication chart for all current oil quality, viscosity recommendations and change intervals. The drain plug has a magnetic insert to remove metal particles from the oil. This must be cleaned prior to refitting. The oil level plug is here. When the level is correct, the oil should be in line with this lower edge and be felt on the threads. The next transmission variant to be considered is the ZF4 HP500 fully automatic. Before proceeding, however, with the maintenance routines, let's briefly consider the basic design and function of the gearbox itself. The HP500 is a 4-speed, fully automatic gearbox, the drive system of which comprises a compound epicyclic gear train and a series of hydraulically engaged multi-plate clutches, which lock the various members to create different reduction ratios. Contained within the base of the gearbox is the main hydraulic valve block and the electrical solenoid valves which control gear selection. Gear shifting is controlled by a separate computer-controlled panel, which is designated EST18. The control panel receives information about road speed and engine speed from two sender units in the gearbox, one on the output shaft and a second on the input turbine. Throttle position and engine load are indicated by a load sender unit connected to the throttle linkage. There is the gear selector switch, which transmits the relevant gear and program instructions. Finally, there is the kickdown switch, which allows a lower ratio to be selected where conditions demand performance driving or hill climbing. With performance driving, the signal to the control panel from the kick-down switch will result in upshifting at higher engine speeds than normal. The drive from the engine enters the gearbox via a torque converter, which incorporates a lock-up clutch to preserve fuel economy. When D is selected, EST18 control will engage lock-up automatically, while accelerating from standstill in first gear. The engine speed at which lock-up occurs will, however, vary depending on load and throttle position. Once engaged, lock-up will remain engaged during all subsequent upshifts. Also featured in the HP500 is an integral hydraulic retarder, which supplements the main vehicle braking system. The retarder is activated by the stoplight switch, which is controlled by this air modulator valve mounted on the foot brake valve. The level of retardation force is dependent on air pressure delivered by the modulator valve, which can be varied between 0 and a maximum of 3.2 bar. It is important to note that this pressure is delivered over the first 9 degrees of pedal movement prior to service brake application. An oil pump driven by the input shaft supplies oil pressure to activate the gears and provide lubrication to the gearbox components. Gearbox oil temperature is controlled by an oil cooler unit, with filtration being provided by an internal oil filter positioned on the suction side of the oil pump. One of the major benefits of an automatic gearbox is that driving is made easy, with the control panel making the decisions on the most appropriate gear shift points depending on the conditions. However, before being able to drive the vehicle, certain vitally important information must be known and acted upon. First of all, neutral on the gear selector switch must be selected before the engine can be started. The inhibitor relay controlling this is built into the electrical distribution center. Once the engine is started, to move off, one of the drive options must be chosen, either D, 1, 2, or R. It must be noted that the brake pedal must also be depressed at the same time as the gear selector button is pressed. This will allow full gear engagement and drive to be authorized. This action sends a voltage signal from the stoplight switch to the gear control computer. This is a safety feature to prevent unauthorized gear selection when the vehicle is stationary, with the park brake released and the driver not in attendance. It must also be noted that certain gear selector buttons are interlocked. Should, for example, position R from D be required, N must be selected first, which places the switch in neutral. Be aware that only when the vehicle is at a complete standstill should reverse be selected. With the foot brake pedal pressed, then released, the vehicle will now fully engage and drive in reverse. Maintaining ZF4 HP500. Moving now to the maintenance on the gearbox. In order to carry out an oil and filter change, the transmission should be at normal working temperature. The main drain plug is located here. To gain access to the filter, remove this cover plate and withdraw the filter element. Ensure that the O-ring on the replacement filter is in position. Offer up the filter, then push it into position. Replace the O-ring on the cover and refit, torquing the retaining bolts to 22.5 Newton meters. It should be noted that because the oil filter is on the suction side of the pump, it is essential it be replaced at the recommended intervals, as a blocked filter would result in serious internal damage to the transmission due to progressive loss of oil pressure, causing gear clutch slip and loss of drive. To refill the gearbox with oil, initially add 15 litres. Start the engine and allow to idle, and then top up until the oil level is between these two marks. To complete the oil filling procedure, bring the gearbox to its normal working temperature of approximately 80 degrees centigrade. With the engine at idle, the oil level, when correct, should be between these two marks. This final procedure is known as a hot check and is the only accurate method to establish the precise oil level. While checking the oil level when hot provides the most accurate level indication, a cold check also offers a provisional guide, as the level must be between these two marks for it to be considered safe to start and drive the vehicle. Where a cold check reveals 10 millimeters or less, as shown here, the vehicle must not be driven. The reason for the low oil level would then require to be investigated and rectified. As mentioned earlier in this program, the load sender setting must be checked with the throttle at both idle and at full throttle, at which points these setting blocks should precisely align. Remember, any setting position on this unit other than these will give the control system incorrect throttle information and affect gear shift quality. If the load sender is badly out of adjustment, similar to this example, the control system will inhibit any gear selection. Engine idling speed should be set to give 500 RPM with the gear selected and in drive. With the park brake applied, this speed enables adequate lubrication to be maintained within the gearbox. With the ZF-HP500 control system, the ESD18 computer panel has the ability to detect certain transmission faults. For example, it will detect transmission failure due to gear clutch slip in drive or during gear changes, or a speed signal failure from the turbine sensor. With these conditions present, the driver's gear selector switch lights will flash continuously, indicating the seriousness of the fault. Where these conditions are present, the fault must be immediately investigated and rectified before the vehicle re-enters service. The control system is designed to record up to 55 faults and store them in the panel's memory, and also the number of times that fault has occurred. To extract this information from the panel, this test kit, known as the Moby-Dick 200, is plugged into this lead, and by operating the fault diagnosis program, a fault code will be displayed here, and the number of times the fault has occurred. By cross-reference to the manual, the fault area can be identified so that action can be taken to rectify the fault. To complete the transmission module, now let's look at the rear axle. The B6 is fitted with a single reduction spiral bevel differential unit, which is available in 4 ratios to suit different operating requirements. From the maintenance point of view, the upper plug is a combined level and filler plug. Whilst in this area, ensure the axle breather is clean. Failure to observe this will cause the axle to become pressurized when hot, resulting in oil leakage from the differential pinion seal or alternatively the hub seals.